All right, line Y1, synchronous motor operation. We are going to go and take a look at synchronous motors as capacitors at this point. Just because we know that we do have that capability of overexciting these things so that we can go and drive them into that point where we are going to go and have a leading power factor. And we talked about that in the previous video. Just really briefly, all that we have to do is we have to go and decrease the resistance so we can let more current through, and then we can get to this overexcited field. And when we get to the overexcited field, it is going to go and adjust what happens. We're adding a little bit of extra overexcitation, which means we are going to generate a little bit of extra counter EMF. And that extra counter EMF is going to go and pull this resultant over the resultant amount of voltage, and because the resultant amount of voltage is going to be tied at 90 degrees to my current, I'm going to be able to go and pull that current above the line. And by above the line, I mean past where my voltage is at. And as soon as I've got current that leaves my voltage, I am looking at a capacitive type of component. We can use these things to go and deliver capacitance alone, in which case we would just use them as a synchronous capacitor. They would have no output shaft at that point. Or I can use them to go and deliver load at the same time as delivering as overexciting so that I can go and deliver my capacitance as well. It's really up to us how we are going to go and utilize these. So let's go and take a look at some examples. I'm going to go and probably solve a little different than what the book does. I'm not bothering to look at the book. I'm just going to solve for what they have inside of here using a lot of the shortcuts that are available inside of my Sharp EL calculator. It is our standard calculator, so might as well be able to go and use it properly. So the first one that they give us here is just going to be an industrial plant with a 600 volt three-phase load of 1500 kVA with a lagging power factor of 60%. Neglecting all the losses, calculate the total kilowatt, the line current with no power factor correction, and then kVA capacity that we would need to have. Now, inside of your book, they give you this drawing. They don't give us this drawing immediately. We have to go and solve for this drawing ourselves. And they want us to go and find total kilowatt load to begin this with. So we're going to start by finding the kilowatt load, which would then allow us to go and find the kVA, and then from that we can Pythagoras over to the kVARs. Or if you're like me, you're just going to take that total kVA, we're going to go and put it in at its phase angle, which is the inverse cosine of 0.60, and get my calculator to spit out my x and my y coordinates. I'm going to start with that. I'm going to go and take my total amount of kVA, 1500, and I'm going to go and put it in at the inverse cosine of 60%, because we know the inverse cosine of our power factor is our angle. Angle is equal to the cos -1 of our power factor. Like that. Let's go ahead and do that. 1500. So I'm going to first put myself into the proper polar mode there. And this one here. I'm into my polar mode here right now, 1500. Clear that a second. Let me just 1500. Too many zeros. Angle, inverse cosine, second inverse cosine. I like putting on all my extra brackets. You guys know that at this point. 0.6, like that, which spits out a value of 1500, and then it's going to go and tell me, if I do the comma over here, that it's going to be at 53.13 degrees. I'm not really concerned about that 53 degrees. What I want to do is I want to do this conversion now to my xy. My xy, the first value that comes out is my 900, which is going to become my x value that I'm going to go and have. And then the second value, my j operator, is going to be my y value, so 1200. So I've just shortcutted the system over here. By shortcutting the system, I'm able to instantly, off of just punching that in there, calculate the total amount of kVARs and the total amount of kilowatts. Otherwise, the system that you would have to go through is you would have to go and take your VA times your power factor to get your watts, and then you would have to go and use your watts and your VA together, and you'd have to go and Pythagoras that to go and make this thing operate. So we're not going to bother with that one. I'm not going to go through theirs. I just don't see the need to go through extra steps when I can go and do everything so sleekly. So we've got our total kilowatt load right now. It's 900 watts. And ultimately, we are still going to go and have 900 watts no matter how we go on power factor correct. A little bit of power factor correction, a lot of power factor correction. The one thing that never changes is going to go and be my watts. Line current initially is going to be found by me taking my VA and dividing it by my E line times root 3. So I'm just going to go and do that to figure that out, 1500 VA. And so 1500, I'm going to put it in as the full VA. This is 1500 kVA that we have over here, divided by my value of voltage, which is going to be 600, times root 3, which is going to get me to a value of 1,443 amps that I'm going to be delivering initially. 1,443. Perfect. Okay, so if I wanted to go and take what I have existing in this plant, which is this existing triangle over here, and correct that all the way down to unity, what I would need to do is I would be able to have to ixnay all the k-bars over here, remove them. So the size of synchronous capacitor that I would need to go and have would have to be 1200 k-bars, right? If I would put in a capacitor that pushes back in the opposite direction, I'm going to push it all the way down, which would mean I would need to have 1200 k-bars to go and remove that. If I would go and remove all that I would have left at that point by taking out all of the k-bars, I would have collapsed the kVA. The only thing I would have left would have been 900 kilowatts of actual load. So I could then go and figure out what my line current would be off of that, which is just going to be my total amount of power, watts divided by my voltage, E line. I'm using watts down because it's the only thing left inside the system, times root 3. So we could just quickly check that one out there. We'll go and take in 900,000. That's a 6. We need this one here, 900,000 divided by 600 times root 3. Gets me to a value of 866 amps. So 866 amps, that's a fairly significant drop for me to go down to there. If I take a look, this over here was 1443. Now I'm going down to 866. That's about a 500 amp drop. You can put a significant, especially at 600 volts, 500 amps at 600 volts, you're looking at about an amp of horsepower. So you can almost add another extra 500 horsepower to your plant now because you have freed up that room on your system. What size of a kVA capacity would I need to correct it to a 90% lagging power factor? So if I don't want to overexcite. Now, first of all, I'm just going to be straight up honest with you. If you could go and correct this thing, you would not want to go and overcorrect. You would not want to go to this 100% because if then you would be slow on the uptake, that all of a sudden you would lose some more lagging loads and you still had this amount of k-bars in the system and you didn't adjust the synchronous condenser, you can go into a leading one. And you wouldn't want that because then you're going to go and get massive bills from BC Hydro on your metering. They monitor for all of that. So what I'm going to do is I'm going to take it to a more realistic one, which is going to be somewhere here at 90%. At 90%, I have no clue what I'm going to go and have yet. All I know is that I'm going to have a 90% power factor and 900 kilowatts. So what I'll do is I'll go and use those kilowatts and at 90% to go and develop a new kVA. So I'm going to go and take my 900,000 watts, I'm going to divide it by 0.9, right? Watts divided by power factor is equal to my VA that I'm going to go and have. Punch that into your calculator. 900 divided by 0.9 gets us out to 1,000. So I would need to go and have 1,000 kVA that I would have left on there. What I'm looking for now is I need to go and find the difference between what I would have had originally down to what I'm going to go and have over here. So if I've got 1,000 kVA over here, and that 1,000 kVA is at with 900 kilowatts over here, I should be able to go and figure out what size of a triangle I'm going to go and have left. You can just use Pythagoras for this one because you've already got two values over here, or you can go and use your 1,000 at the inverse cosine of 0.9, which would also spit out your triangle over there. And if you would do so, you would find out that you would be at this value over here of 436 kVars that we would have left inside of the system. So if I'm going to leave 436 kVars in the system, and I originally had this value over here, which was going to go and be that 1,200 kVars, right? We see I saw this 1,200 up top here. I need to go and take away a certain amount of kVars in order to get to the 436. All I'm going to do is going to take my 1200 minus my 436, and when I do that, it's going to tell me the size of the capacitance that I need to go and run this thing at, and that's going to tell me that I need this thing at 764 kVars leading for this. So we're just going to overexcite. We're going to monitor the overexcitation until we see that we have got this 764 leading kVars. Perfect. It's a lovely system because, once again, we don't have to have individual capacitors. All we need to do is we need to go and overexcite this. Just change the value of current inside of this field rheostat. And as long as I go a little high, a little low, I can just make any power factor that I want off of that system. You do still have to have a synchronous condenser that's able to go and supply what you need. For this one over here where we said let's go and correct it to a unity power factor, I would need to have a synchronous condenser that would have been over 1200 kVars if I wanted to go and take that thing all the way down. Same with this one over here. You would still need to have something that's going to be rated as far as synchronous condensers go, that this thing is going to be good for up to 800-900 kVars if I wanted to take 764 out of this thing. Okay, last one that we have over here is going to be a motor that has a load of 1200 kilowatts at a lagging power factor of 75%. And then we're going to go and install a synchronous motor to supply a 300 kilowatt load and provide power factor correction to the plant. And I need to take the power factor down to 92% lagging. So what's the minimum kVA rating required for this new synchronous motor? This one is a bit more complicated of a calculation. These type of calculations are going to require two parts. First of all, we have to go and figure out what we have existing. Once we know what we have existing, then we have to go and figure out what we are going to add and how that's going to go and affect it. Now, ultimately, we know one thing about power factor correction. That thing is that anytime that we power factor correct, it is the watts of our system that are going to go and stay the same. So we're always going to find watts as a baseline. They give us this plant over here that it's got a load of 1200 kilowatts at a power factor of 75%, which is going to go and give us, a bunch of other stuff that we can go and calculate off of that thing. Now, when we do that calculation, it's going to go and tell us a couple of things about the plant. First of all, we do need to go and find out how many kVars we have inside of that plant. As much as I would like to just take this 1200 kilowatts and work directly off of it, what we're looking for in the very first calculation is this value of kVars, because that value of kVars is going to go and tell us that, what we need to go and take out later on. We are going to add this one in a minute. So let's start by finding this thing. 1200 kilowatts, if I go and take my 1200 kilowatts and I divide it by my power factor, so watts divided by power factor is going to go and equal my VA. So I'm going to go and take that 1200 and I'm going to go and divide it by my 0.75. And when I go and take 1200 divided by 0.75, that's going to go and take me out to a kVA of 1600. Once I have got that 1600, two ways that I can go and figure out, what the side this one is going to go and be. I can either go and use the 1200 kilowatts, the 1600 kVA, and I can then go Pythagoras. Or if I want, I can go and take that 1600 kVA and I can just go and put it in at an angle. I'm going to go do that because that's the way that I prefer to do these things. Doesn't have to be the way you prefer, but I'm going to go 1600 at angle. And then I'm just going to go and put in an inverse cosine of 0.75, 75%. And then that is going to go and give me values over here because we're in XY. You see the XY up there. First value gives me the X. The second value that's going to give me is going to be the Y. So I'm going to have 1058 as my Y value. We see that then over here. So I'm going to draw that in. At this point, I'm going to ignore this 1600 kVA because that's going to go and change. I'm going to go and hold on to this 1058 because that I know is going to have to be there. What I will do now is I am going to go and take a look at what happens when I add on my 300. So basically now what I'm going to do is I'm going to go and add on this 300 kilowatts of the motor over here. When I add on that 300 kilowatts of the motor, I'm also going to go and have to add on some sort of kVars to go and knock this thing further back. So let's start by adding on this over here, and we're going to find out what our new overall triangle would be if I'm going to go and have 1200 and 300 plus, 1058. So we'll start by adding on this 300. 300 plus 1200 means that this total bottom, my total amount of kilowatts in the plant, are going to become 1500 kilowatts, okay? We'll white this out here. We'll say 1500. 1500 kilowatts. I'm still going to go and have the same K bars. I don't know what I'm going to go and have for a power factor at this point. And I'm not really too concerned yet what I'm going to go and have for a power factor, because I know that ultimately I'm looking for a target of 92%. So for me to go and find a target of 92%, I'm just going to go and take this 1500, my watts, divided by my power factor. In this case, it's going to be my desired power factor that I'm going to go and have. And I'm going to go and figure out what that gives me for a new target VA. So 1500 watts divided by a power factor of 0.92 tells me that I'm looking to go and get a total kVA of 1602. Note how close 1602 is to the original 1600 kVA that I have on my plant, right? What we're trying to do is we're trying to add stuff in without going and having to change up our service. So we're fixing our power factor in order to go and do so. So this new target is going to go and become 1602. If I'm going to go and have a triangle that, 1630 that I'm going to go and have, saying that wrong, 1630, 1630. What this is going to do is this is going to go and create a new triangle for me. And the new triangle is going to go and look like this. If you go and once again Pythagoras, because we have that value of 1630 and we have that value of 1500 kilowatts, we'd find out that ultimately at the end of the day, what our plant should have left for kVARs is going to be this value over here of 638. Now we know that's not what our plant started out with. We know that our plant started out with this value over here, which was 1058 kVAR. And we're now going to drop it down to 638 kVAR, which means that we're going to be chopping off that top section. How do we chop it off? Well, we are chopping it off with this synchronous motor that we have over here. So if we've got 1058, then 638 left, all we need to do to find the size of our capacitor is we need to go and subtract 1058 minus 638. And then that is going to go and give us the size of cap that we're placing in over here. In this case, we're not actually using a cap, we're using the condenser to go and do that. Tells us that this is going to have to be a size of 420 kVARs over there. Okay, so now we have got our kVAR rating. What this tells us is that we know exactly what setting we need to go and have on our motor. We know that this motor needs to go and supply two things in order to go and fix this plant and supply the new load. We know that the motor is going to have to give us the 300 kilowatts, as well as it's going to have to go and give us 420 kVAR. So we can just create a new triangle in the opposite direction, 300 kW, 420 kVARs leading that we are going to go and have in the opposite direction, which we would then be able to, once again, if we wanted to, we calculate that kVA. In all honesty, what you're going to do is you're going to go and take a look at the overall capacity of that that unit. In this case, you can do the math. It comes out to 516 kVA. But what you would be looking for is you would be looking for a unit that would be able to go and supply your kVARs and your kilowatts at this type of a power factor. You're not going to go and make those adjustments right away. What you'll end up doing is you're going to put this thing onto the system. Once you have it onto the system, then you are going to go and start running it and adjusting it, just cranking up the current that you are going to go and have through that synchronous field. And as you crank that current up that you have going through that field, the DC field, you're going to just watch your overall power factor off of this thing. Anyways, it's a pretty fantastic little system. It's a great application for how we can go and utilize these not only to go and deliver actual physical load, but also to go and deliver all the necessary kVARs that we have, and we can do that and continuously vary it just by adjusting a small value of current. All right, that is it for this one.